Greetings, Dr. Dan here from Optimal Optics with Unit 2, Light as a Particle. Now, you might be saying to me through your computer, Dr. Dan, you just spent Unit 1 proving conclusively that light is a wave, and now you're telling me light is a particle. What's wrong with you? Well, my answer is, first of all, stop yelling at me. And second of all, when light or any particle gets down to the size of photons, matter acts in weird ways. And it can act like a wave in certain circumstances, and it can act like a particle in other circumstances. My high school physics teacher, Mr. Lester Siegel, called light a wavicle to emphasize its dual nature. It can act as a particle, it can act as a wave. Today we'll talk about light as a particle. So let's create a point source of light, sending light rays out in all directions. And let's step away from the light, let's say 10 feet away. As you get further away, if you look at a bundle of light, and the light rays in it, they appear to be getting a little less divergent or a little more parallel. If you get a little further away, let's say 15, they get even more parallel. And at 20 feet away from the light source, the light rays are parallel. May not quite appear that way, but I've already told you about my artistic ability. So at 20 feet from the light source, rays are parallel. Another term for parallel rays of light is called collimated light. C-O-L-L-I-M-A-T-E-D. It occurs at 20 feet away. 20 feet is the same thing as 6 meters. And we call that distance, 20 feet or 6 meters, optical infinity. Now let's create a transparent optical surface. And I'll draw an optical axis. I'll define optical axis a little later in this unit. And let's place an object on this optical axis. And we'll send a couple light rays out from this object. And this transparent optical surface will converge the light to a point on the other side. And that point is called a real image of that object. It's a real image because the light rays actually do pass through that point. If you put a screen there, you would find the image formed on the screen. Now let's construct another transparent surface. And our optical axis, and our object to the left of the surface, and construct our 2 light rays again, coming from that object. But this optical surface bends the light away from the optical axis. Now, if you're standing on the right side looking at the optical surface, you will notice that the light appears to be coming from this point here, if you extend those light rays back. But the light doesn't actually come from that point. Therefore, that's called a virtual image. Important concept in geometric optics, real images versus virtual images. So if you put a screen there, you would not see an image on that screen because the light does not actually come from that point, but it looks like it does. Hence, it is virtual. Now, there's something called the rectilinear propagation of light, and all that means is that light travels in straight lines, which we call rays. We can prove this in a couple different ways. One is with a pinhole camera. I have another video on my construction of a pinhole camera from a few years ago when there was a solar eclipse. I made a little bigger hole than a pinhole just because the ruler tool on this whiteboard isn't quite accurate and it might be difficult to get the lines to actually pass through a small hole. This is our arrow object, and if we extend the light ray from the top and the bottom, you'll see that the image is upside down. The top of the image becomes the bottom, the top of the object becomes the bottom of the image, the bottom of the object becomes the top of the image. We call upside down images inverted images. It's a term you'll see often in geometric optics. The other proof of the rectilinear propagation of light is the creation of shadows. So we'll create our point source of light again that sends light rays out in all directions. And we'll construct an opaque obstruction at some distance from the light source that will block those light rays. We'll construct two light rays, each one going to the edge of this obstruction, and everything behind the obstruction is going to be a total shadow. And we call a total shadow an umbra. U-M-B-R-A. Now, let's contrast that with a bigger source of light. Let's separate this into our new diagram with a larger source of light. We'll call that a diffuse source of light. And we'll create our opaque obstruction. And now you'll notice when we send light rays from the top and bottom of this diffuse light source toward the edges of this opaque obstruction, some light does get behind it. So directly behind the obstruction, that's still our umbra, our total shadow. But you'll notice in this area here and the other area corresponding underneath, partial light gets there. Those are partial shadows. And we call a partial shadow a penumbra, P-E-N-U-M-B-R-A. Now here's some important definitions. The optical axis is an imaginary line through the centers of curvature of an optical system. A light ray along the optical axis is perpendicular to the optical surfaces and therefore is undeviated. You'll notice that optical axis that I drew previously was a straight line. There were no deviations. Paraxial light rays are those light rays that are near the optical axis, and the chief ray is closest to the optical axis. Chief Ray was also the head of the Brooklyn Indian tribe, but I digress. We define light in this course as traveling from left to right, and we call that a positive direction. Distances also, if they're measured from left to right, are positive, but if they're measured from right to left, they are negative. So here's a line, we're defining it as going from A on the left to B on the right, and we're saying it's 4 inches long. So if you're talking about line segment AB, that's 4 inches. But if you define the line segment as BA, going from right to left, you have to say the distance is negative 4 inches. Really important in geometric optics. Speaking of shadows, one of my favorite shadows that I can produce is a shadow of a dog. And it's done by taking one hand, sticking the thumb up, that's one of the ears, taking the other hand, draping it over the first hand like that, and sticking the thumb up. So now you have our two ears, and the pinky is the mouth.